Hello guys, in this video I'm going to continue speaking about column chromatography, and I will be mentioning especially ion exchange chromatography. I will be speaking about the principle of ion exchange chromatography, how to perform it, and everything in detail. So if you are interested to know more about ion exchange chromatography, watch till the end. As I told you in the previous video, when we say column chromatography, we might be mentioning several types of chromatography. In the previous video, I mentioned adsorption chromatography and its automated technique, the HPLC. And in this video, I will be speaking about ion exchange chromatography. First, ion exchange chromatography is like other types of chromatography, so it's a separation technique. So we use it to separate proteins or other types of molecules from each other. Now, when we speak about chromatography, we should always mention the stationary phase and the mobile phase as usual. So in ion exchange chromatography, the stationary phase is a resin, is solid. It's a resin forming polymer or network. It can be cellulose or agarose or any type of resin, but the important thing is that on this resin there should be charged molecules, covalently bound charged molecules. In ion exchange chromatography, charge is very important because ion exchange chromatography depends mainly on charge. So the stationary phase is solid, and the mobile phase, so the stationary phase looks like this. A resin holding substance A, which is charged molecules. The mobile phase is a liquid. It's holding our sample, and it's a liquid. And in the sample, in our sample, there should be also charged or polar molecules like proteins, amino acids, or nucleic acids. So yeah, ion exchange chromatography is all about charge. Now, first, in order to speak more about ion exchange chromatography, you should know that in ion exchange chromatography, there are two types: cation exchange chromatography and anion exchange chromatography. In cation exchange chromatography, the substance which is covalently bound to the resin, which is substance A, is negatively charged. And this substance is bound to substance B, which is positively charged. It's like this is a polar bond, or an ionic bond. And then the substance of our interest, our substance we need to separate in the sample, is positively charged, and then it will be exchanging with substance B. So because of this, we call it cation exchange chromatography. In anion exchange chromatography, it's the opposite. So substance A is positively charged, it's bound to substance B, which is negatively charged, and then the substance of our interest is negatively charged, and it will be exchanging with substance B. Now, let's say this is the column. So this is the column, this is the resin, substance A, and then substance B, which is positively charged. So this is a model of cation exchange chromatography. We need to apply, as I told you, in our sample there should be charged molecules. Now, in order to perform ion exchange chromatography, there is a very important factor you need to know, and you need to take it in, like you need to think about it. It's pH and pI. Proteins and amino acids in general are zwitterions. And what zwitterions mean? It means that they can either be negative or positive according to the pH of the solution. So let's see how. This is an amino acid. It has an amino group, a carboxy group, and a side chain. The amino group and the carboxy group can be either ionized or deionized. So amino and carboxy group can be both protonated or deprotonated. So this is the amino acid. If we go to lower pH, in lower pHs, in acidic pHs, we have a lot of hydrogen ions in the solution, which are like protein ions. hydrogen ions are protons. And in this case, when we have a lot of protons in the solution, so both the carboxyl and the amino group will be protonated. But when the amino group is protonated, it will be holding a positive charge. But when the carboxyl group is protonated, it will be deionized. And in this case, the amino acid will hold a positive charge. The opposite happens when we have a higher pH, in which we have a hydroxyl groups in the solution, and then both the amino and the carboxyl group will be deprotonated, and then the carboxyl group will be holding a negative charge, while the amino group will be holding no charge. So the amino acid in general will be holding a negative charge. This is what zwitterions means. So the amino acid can be both negatively or positively charged according to the pH of the solution. The pH in which all the amino groups will be protonated and the carboxyl groups will be deprotonated, we call pKa1. And in the pH in which the amino acid will be holding a negative charge, we call it pKa2. If we take the very middle point between pKa1 and pKa2, when half the amino groups will be positively charged and the carboxyl groups will be negatively charged, so the amino acid will be holding a zero charge. It's called the isoelectric point, and this is very important. So the isoelectric point is the pH in which the amino acid will be holding a zero charge. This is what we call the isoelectric point. The net charge of the amino acid will be zero. The same is applicable to the proteins. Now, you might think that an isoelectric point of a protein is a pH on which all the amino acid in the protein holds a zero charge. This is not true. This is not right. So the isoelectric point of a protein, now you know that the protein is a chain of amino acids. When a protein holds a zero charge, it means that half of its amino acids are positively charged and half of its amino acids are negatively charged. Let's say we have a protein of 100 amino acids, then 50 of them will be positively charged and 50 of them will be negatively charged. In this point, the protein will be in its isoelectric point, because in this point the protein will be holding a zero charge. Now, every amino acid has a different isoelectric point. Let's say I took like a glutamic acid as an example, because glutamic acid and all the acidic amino acids are special because it has also a carboxy group in its side chain. So if we increase the pH, this carboxy group on the side chain will be negatively charged because it will be deprotonated, and then the amino acid will hold a negative charge. If we further increase the pH, the amino acid will hold a -2 charge. But when we decrease, so in lower pHs, both the carboxyl groups will be protonated, so they will hold no charge, so they will be deionized, and then the amino acid will be protonated, so it will be ionized, and then the amino acid will hold a positive charge. If we look at the pH gradient, so this glutamic acid will have 3 pKa's, pKa1, pKa2, and pKa3, because it has another thing on the side chain. If we look to the pH gradient, this is pKa1 of glutamic acid is 2.19, this is pKa2 and pKa3. And then, as you see here, the isoelectric point is the middle point between pKa1 and pKa2. So you might be asking, so how can we know the pI of different amino acids? Actually, it's known. All the pKa's of different amino acids are already known. So you can find a table like this. in which you can find the pKa1 and pKa2 of all the amino acids. Of course, some amino acids have pKa3, like glutamic acid, for example. So what you should know to know the isoelectric point is simply pKa1 plus pKa2 divided by 2, because it's the very middle point between pKa1 and pKa2. Now let's go back to ion exchange chromatography and how to perform it. Before everything, in order to perform ion exchange chromatography, we should choose between cation exchange chromatography and an ion exchange chromatography. How does it happen? It depends on the protein I need to separate. So let's go to pH gradient. pH gradient, let's say between 1 and 10. And then if my protein has a certain pI or isoelectric point, let's say of 5, for example, if the pH of the solution is lower than 5, then our protein will be negatively charged. And then if the pH is higher, then our protein will be positively charged. And in this case, we should apply ion exchange chromatography. And when the protein is positively charged, we need to apply cation exchange chromatography. So saying that our protein has a pI of 5, let's say, and we have another protein who has a pI of 7, then if I take a lower pH, for example, or for example, if I choose a pH of 6, it's here, then this pH will be higher than the pI of our protein, and then our protein will be negatively charged. But this pH will be lower than the pI of the other protein, saying that the other protein has a pI of 7. So the pH will be lower than the pI of the other protein, and then the other protein will be positively charged. And in this case, we should apply anion exchange chromatography, because in this case, our protein will be negatively charged. You should I know it might be a bit confusing. There is like a rule of thumb. When the pH is higher than the pI, then the protein is negatively charged. And when the pH is lower than the pI, then the protein is positively charged. This is a rule of thumb. Now let's see how to apply ion exchange chromatography. Let's say we choose anion exchange chromatography, and I will tell you why did I choose anion exchange chromatography. Let's say I have a sample. In this sample, I have proteins, and the protein of my interest has a pI of 2. In this case, I should choose the right pH in order to be able to separate my protein from the other proteins. So when I choose a pH, so here, if you look at this, here the pH is 2.3. So the pH is higher than the pI of our protein of interest. And then, as I told you, the rule of thumb, when the pH is higher, then the protein will be negatively charged. So my protein will be negatively charged, and then I should apply anion exchange chromatography. So when I apply my sample to the column, my protein will be exchanging with substance B. In order to understand this better, let's take a look at the pH gradient. The pI of my protein is 2. And then if I choose a pH higher than the pI, 2.3 for example, then my protein will be negatively charged, okay? But the thing is that all the proteins who have pI higher than 2.3, all the proteins who have pIs in this range, they will be positively charged. Why? Because all the protein who have pI higher than 2.3, the pH of the solution will be lower than their pIs, and then they will be positively charged. Yeah, as I told you, to understand this, you should also apply the rule of thumb. pH higher than pI, it means that the protein is negatively charged. pH lower than the other pIs, it means that all the other proteins will be negatively charged. Positively charged. And then when we apply this solution to the column, only my protein, which is negatively charged, will be exchanging with substance B. So let's say, how does it work? This is the column. I applied the solution. This is my protein. The protein will compete with substance B. Substance B will be washed out with the other proteins who are holding a positive charge. These are the proteins who are holding positive charge. And this is substance B who is washed out because my protein took its place. Now I have the column and my protein is stuck in the column. Now the question is how to elute my protein from the column. There are two methods to elute the protein from the column, either pH or salt gradient. pH is very easy. Why? Because let's say in this case we have cation exchange chromatography, so the protein is positively charged. All that I have to do in order to elute my protein, you have to guess actually. We have to apply something related to the pH gradient and to the isoelectric point. You should guess. So yeah, my protein is positively charged. Why? Because the pH of the solution is lower than the pi of the protein. Then the protein is positively charged. Now, if simply I apply a solution, so this is the pi, and when the pH is lower than the pi, then our protein is positive. Now, if we simply apply a solution that has a pH that is equal to the pi of the protein, what's going to happen is that our protein will hold a net charge of 0, and then it cannot bind to substance A anymore, and it will be washed out. Why? Because the solution is holding a pH. The solution has a pH that is equal to the pi of the protein. In this case, because the protein binds to substance A, the bond between the protein and substance A is a polar bond or an ionic bond. So when the protein has a net charge of 0, the protein cannot bind anymore to substance A, and then it will be washed out. This is pH. We simply have to apply a solution that has a pH equal to pi of the protein of my interest. Even if there are other proteins stuck to the, let's say there might be some impurities. Let's say some other proteins might also be binding to substance A. When we apply a pH that equals exactly to the pi of our protein, only our protein will be washed out. There is another method called salting out. In salting out, let's say we have different proteins that are all negative, but proteins will have different side chains, and some proteins will bind to substance A with one side chain, or 2 or 3 or more. So binding groups, let's say. This protein has 2 binding groups, this one has 1, this one has 3. If we apply a solution that a salt solution, and if we increase the concentration of the salt gradually, like this, then let's say this is the concentration of the salt. It's the red line here. If we increase the concentration of the salt, what's going to happen is that the salt will compete with the proteins on substance A. And then the protein who has one binding group will be eluted first, and then the protein who has 2 binding groups will be eluted, and then the protein who had 3 or 4 or more. So the proteins will be eluted gradually when we increase the concentration of the salt, and this is called salting out. This salting out can also be used when we are separating nucleic acids. Why? Because nucleic acids are negatively charged. This is a nucleic acid chain. It has deoxyribose sugar a nitrogen base, and a phosphate group. So nucleic acids are always negatively charged. But then nucleic acids have different chains. So when, for example, when the nucleic acid has one, let's say one nucleotide, it will be washed out first, and or eluted, let's say it will be eluted first, and then the nucleic acid who has two, let's say two nucleotides and then three nucleotides will be will be eluted then. So salting out can be used also to elute our protein or our nucleic acid from the column. This is everything I wanted to tell you about ion exchange chromatography. I hope you enjoyed this video and you get like interesting information from it. If you really enjoyed the video, please don't forget to like, share, and subscribe the channel. If you have any questions, don't hesitate to leave your question in the comments. I will answer you. And yeah, and have a nice day. See you in the next video. Bye.